So this is our first lecture video on Chapter 24, where we will be looking at transition metals and coordination compounds. So I just want to kind of start off this chapter with this little cartoon. So you see this guy in the lab and he's got these atoms coming in, and these atoms says, "You the guy who just made a 7-coordinate compound of chromium-3? Well, we've got a message for you. Chromium-3 doesn't like being 7-coordinate. So the little caption of the video is, "Late that night, Professor Robinson's laboratory was overrun by hostile elements." So one of the things that we'll learn and why this little cartoon is funny is that a lot of the transition metal elements prefer to be in the +2 oxidation state. And that's one of the common oxidation states for a lot of the transition metals, even though they can have multiple oxidation states. So I just want to start off by addressing what are some of the things that we should be able to do after the end of this chapter. Well, one of the things is we want to be able to do is that we want to be able to write the electron configuration of the atoms and ions of the D block metals. And we also need to know that chromium and copper have exceptions. We also want to be able to identify trends and key properties of the transition metals, define and distinguish among the various types of magnetism. So what's paramagnetic, what's diamagnetic, what's ferromagnetic. We also want to explain why transition metal complexes are colored and why we see certain colors associated with them. We should also be able to recognize the correct name or formula of a coordination compound if given the formula or the name, so vice versa. We also want to be able to define and apply the definitions such as what is a complex, what is a ligand, what is a coordination compound. We also want to be able to determine the oxidation number of a metal in a complex, and we also want to be able to determine the coordination number of a metal in a complex. Then we also want to be able to distinguish between different isomers and give the geometric isomers that are possible for a given complex. We also want to know that the d orbitals split in a complex and that the splitting pattern varies with the molecular geometry. We also want to identify the 4 factors that influence the amount of d orbital splitting. We want to know what is meant by high spin and low spin and how this can affect the magnetic properties. And lastly, we want to be able to identify applications and the importance of transition metal complexes. So why do we even care? So in our first video, we're going to be focusing on the background information, giving some definitions, looking at periodic trends, and the common geometries that we see for transition metal complexes. So in class, I'll actually do a demonstration for you. And in that demonstration, we'll have a beaker. So in that beaker, I'll have a solution of nickel chloride. And in solution, that nickel chloride doesn't have the chlorides bound to it. You have 6 waters bound to it, and the solution's green. But then I'm going to start titrating in ethylene diamine. And ethylene diamine is a ligand. And as I start adding the ethylene diamine, we'll see 3 different color changes. We'll first see a light blue color, then we'll see a royal blue color, and then finally we'll see a violet color. And then no matter how much ethylene diamine that I add, it won't change any color other than the violet color. And the ethylene diamine that I'll be adding will be colorless. So it'll be cool to see the green thing turn light blue by adding something that's colorless, and then adding even more it turns royal blue, and then it turns violet. So these changes in color are due to the ethylene diamine binding to the nickel. So as one ethylene diamine binds, so there's one bound, the nickel complex turns light blue, and then as we add 2, it'll turn the royal blue, and then as we saturate the compound and have 3 ethylene diamines bind, it'll turn violet. Now, ethylene diamine is a ligand that contains a nitrogen, a carbon, another carbon, and another nitrogen. And that both of those nitrogens have lone pairs. And I'm going to put the hydrogens on there. So it's these lone pairs that bind to the metal. So they donate to the metal to make a complex. So there's the nitrogen there, and it's bound to our metal center right here. So it makes that bond right there. And ethylene diamine is a special type of ligand. It's called a chelating ligand. And that chelating ligand means that it binds in two spots or more than one spot on a metal. So the ethylene diamine is a bidentate ligand. So it has two places where it will bite or coordinate to the metal. And sometimes when we discuss chelating ligands, we'll ask, well, what's the bite angle? What's the angle created when that ligand binds to the metal? So that's the bite angle there, that angle between the ligand, metal, and ligand. Okay, so let's just start talking about transition metal complexes. And this is absolutely my favorite part of the course because I'm a coordination chemist by training. And so I've studied a lot of biological systems where metals play an important role. I've studied catalytic processes and where those catalysts are useful for producing certain drugs and certain enantiomers or drugs. And so there's a lot of really cool things about transition metal complexes. So I want you to just kind of think about, what do you know about transition metals? And what do you think about when somebody mentions a transition metal? Well, one of the things that may come to mind if you have any experience with transition metals is that they're usually really, really colorful. So it's the transition metal that gives the ruby its color and the emerald its color, because it has its transition metals stuck in the crystalline lattice that give it the pretty colors. Transition metals also have magnetic properties. They'll either be ferromagnetic or paramagnetic or diamagnetic. They come in different geometries, so things like square planar, trigonal bipyramidal, square pyramidal, and octahedral. They also act as good catalysts because the ligands that bind are labile, meaning they can come off and come on. Then that means the reagent can come in, bind to the metal, do its chemistry on the metal center, and then be released. So a lot of transition metal complexes make good catalysts. Also, transition metals are stable in different oxidation states. So when you were doing your naming section in Chem 1A, you had to look at some of the oxidation states that were available to certain metals and define the oxidation state when you determine its name. Also, the transition metal complexes come with different coordination numbers, so different things bound to it, a different number of things bound to it. So it may have 4 things bound, or 5 things bound, or maybe 6 things bound. So all of these different things contribute to making the transition metals unique. And a lot of these properties have to do with the fact that these transition metal complexes have d orbitals, and they're accessing these d orbitals that have electrons in them. And so the d orbitals, 4 of them have the same general shape where you have 4 lobes, and each one of those lobes are in different phases. It's just they're oriented differently. So the dx squared minus y squared, this lies on the x and y axis. The dzx lies in between the z and x axis. The dyz lies in between the y and the z. And the dxy lies in between the x and the y axis. And the dz squared, that's the funny one of the group. It's got 2 lobes, kind of like a p orbital, but both of those are in the same phase. And then around that, you've got this donut shape around it. So you got a donut in a different phase. So the dz squared has a different shape than the other ones. Now when we talk about transition metals, a lot of times people use the term d block elements and transition metals interchangeably. But in reality, they mean something slightly different. So this is our d block here because we're filling in the d orbitals when we're filling in those valence electrons, those outermost electrons. So remember, this was our s block, this was our p block, this is our d block, and this is our f block. But transition metals, this is an element that has at least one simple ion with an incomplete outer set of d electrons. Because what they mean by transition metals, they want an electron to be there, but have an open space for it to move to, so it can transition or move to another orbital within the d orbitals. So if we look at the periodic table, the transition metals are titanium to copper and hafnium to gold. Now the reason why like zinc and scandium aren't transition metals is they don't have an electron that can transition. So for example, let's take scandium. And I'm going to write the electron configuration for scandium. So scandium is right here on the periodic table. And the electron configuration for neutral scandium is argon 5s2 4d1. But the common oxidation state for scandium is scandium 3+. So scandium 3+ means I have to take away 3 electrons. So if you remember your rules from electron configurations, you take away the s first. So I'm going to take away both of the electrons in the s orbital. So I've taken away 2. Now I'm going to take away the 1 in the d. So the only thing left is the argon noble gas configuration. So there are no electrons in those 4d orbitals. They're completely vacant. So if there's no electron there, there's no electron to transition. Now let's apply that to zinc. So the common oxidation state of zinc is zinc 2+. And if we look at that electron configuration, it would be argon. And so 4s2, 3d10. So that would be the neutral. Now I've got to take away 2 electrons. So I take away the electrons from the s orbital first. So I'm just going to scratch that out. So the electron configuration for zinc 2+ is argon 3d10. So if I look at 1, 2, 3, 4, there are 5d orbitals, and each one of those has 2 electrons. So 1, 2, 3, 4, 5. So I'm following Hund's rule. I'm giving each one an electron before I fill them up. So 6, 7, 8, 9, 10. Well, notice that each one of these spots in the orbitals are completely full, so there's nowhere for an electron to go if it moves. So zinc can't be a transition metal because all the orbitals are completely full for the d electrons. So if all the orbitals are completely full, or if there are no electrons in the d orbitals, then it can't be a transition metal. Okay, so now I want to look at some other definitions. For instance, what is a ligand? And a ligand is either an atom or an ion or a molecule that formally donates electrons to the metal. So it's something that binds to the metal. And as those ligands bind to the metal, they create coordination compounds. So a coordination compound is composed of a metal atom or an ion and one or more ligands. So this entire species here, this cobalt amine complex, so let me write out the formula. So cobalt, and there are 6 amines, and then there are 3 chlorides. So this entire thing is the coordination compound. Now the brackets here tell us what's actually attached to the metal. So each of these amines, so those are ammonia molecules, and when they're attached to a metal, we change the name to amines. So each of those amines that are attached to the cobalt, right here, and this actually forms a complex. So a complex is a coordination compound, and they are acid-base addicts. So everything that's bound to the cobalt is within the brackets. But the chlorides, these are our counter ions, and they're balancing out the charge of this cobalt complex because it has an overall 3+ charge. So I need 3 chlorides to balance out that charge, and this entire thing is my coordination compound. But the part in the brackets, this is my complex. And a complex ion is simply a charged complex. So this amine complex, which has a 3+ charge, this would be a coordination complex ion. Now when that amine, so let me erase what's on my slide. So when that amine binds to the cobalt, so that ammonia molecule has a lone pair, and it donates an electron density to the metal, or let's just go ahead and write cobalt. So the ammonia is acting as a Lewis base. It's donating electron density to the cobalt 3 plus ion. The cobalt 3 plus is acting as a Lewis acid. So this is where we get a coordinate covalent bond. So that's a coordination bond right there. Now the coordination number, that's the number of atoms, but not necessarily the number of ligands bound to the metal. So the number of points of attachment to the cobalt center, to that metal center. So there's one thing attached, 2, 3, 4, 5, 6. So there's 6 things directly attached to the cobalt. So this would be a 6-coordinate compound. The coordination number is 6. Now let me change this cobalt. Let's say if this cobalt was attached to 3 ethylene diamine ligands. So even though there are 3 ligands here, there's 1 ethylene diamine, 2 ethylene diamines, and 3 ethylene diamines, the coordination number for this cobalt complex is still 6-coordinate because there are 6 things, or 6 coordination bonds to the cobalt center. So the number of bonds to the metal determines the coordination number. Now a chelating ligand is a ligand with 2 or more points of attachment to a metal ion, such as the ethylene diamine. And chelates are the compounds that contain chelate ligands. So that name comes from the Greek chele, which means the claw, the crab. So kind of think about where the ligand almost like pinches the metal, so that's where the name is derived from. And the denticity, that refers to the number of binding sites on a ligand. So how many times does a ligand bite the metal? So again, this is just re-emphasizing what a complex is and what a coordinate covalent bond is. So in lab, you will actually be making this compound, and it's a water-soluble complex. So if you have a silver ion in solution and you add ammonia to it, that ammonia is a Lewis base because it's got that lone pair, and that lone pair will donate its electron density to the metal to make a bond. It'll make a coordination bond. So that's a coordinate covalent bond. And this would be a Lewis base adduct. So this is an example of Lewis acid base chemistry. Now here we're just looking at some common ligands that can bind to metals. And what you'll notice that each one of these has in common is that they have a lone pair of electrons to donate to the metal. For example, here with water is a good ligand, so it can donate electron density to the metal. Ammonia, the chloride ion, carbon monoxide, cyanide, and the thiocyanate. And you've already worked with the thiocyanate ion when you did the intro to the equilibrium lab, where you added thiocyanate to the iron complex, to the iron, and it complexed and made the really cool dark blood red or orange color. And then some other ligands. And here are some other ligands. We have the oxalate ion. So this can actually be a bidentate ligand and bind to a metal. Ethylene diamine has 2 lone pairs, so this can also be a bidentate ligand and bind to a metal. And then this very big ligand is EDTA. So if you look at some of your food containers and ingredient lists, you may see EDTA listed as an ingredient. but it has 6 points of attachment. So 1, 2, 3, 4, 5, 6. So this ligand is a very good chelating ligand because the higher the denticity, so the number of points of attachment that a ligand has, the more stable the complex is going to be. And when I say the more stable the complex is going to be, that means the formation constant is much larger. So you get a much larger equilibrium constant, and it's much more likely to form. So this one's very likely to bind or to hold on to a metal complex. So this is just showing you again where the metal can bind to the ligand. So the ligand will wrap around the metal and bind to it. So here we're looking at EDTA and ethylene diamine. So ethylene diamine, there's one of your ligands there, and there's one of your other ligands, and your third ethylene diamine. And with the cobalt, there's only one EDTA ligand, and all 6 sites of the cobalt are taken up. So they both produce octahedral complexes. So you have the equatorial ligands, and then you have 2 axial ligands. So above and below, these are our axial ligands, and these that are in the plane, these are our equatorial ligands. Now something interesting looking at the denticity. The higher the denticity, the more stable the complex. So think of an analogy like this. Let's say you have a person and they're walking, some dogs. But each one of those puppy dogs, I'm not going to be able to draw puppy dogs, or 2 of them are tied together to a leash. And so you're walking a total of 6 dogs, but 2 of those are tied together, these 2 are tied together, and these 2 leashes are tied together. And then you're walking along with your other friend who's also walking 6 dogs. But there's 6 dogs, 1, 2, 3, 4, 5, 6. All of their leashes are tied together. Now you get to talking as you're walking along, and you forget that you're supposed to be taking care of the dogs, and the dogs start running away. Well, which set of dogs, or which person is going to have an easier time grabbing their dogs back? Would it be the person where it has the dogs paired up, or the person that only has to catch 1 dog because all 6 are tied together with 1 leash? So hopefully you said that the person with the 6 dogs all tied to 1 leash would have an easier time getting their dogs back, because once they catch 1 dog, they've caught all 6. Well, the other person that has the dogs on the 3 different leashes, once they catch 1 dog, they'll have 2 dogs, but then they've still got to get the other 4 remaining dogs. So the leash represents the denticity of the ligand. So a leash tied to more ligands, so like the EDTA, is going to have a higher formation constant. So that complex is more likely to form. So it's more likely for the person to grab the dogs all back than if they're all separate. And even imagine, let's say you've got another friend walking a dog, or 6 dogs, but all 6 of those dogs are on completely separate leashes. Well, if that person drops the leashes and all 6 dogs take off running in 6 different directions, they're really going to have a hard time getting those dogs back. So when chemists design ligands and they want to bind a metal complex strongly, one of the tools that they use is they'll create a ligand that is a chelating ligand, so it has multiple points of attachment to make the complex even stronger. Now here's kind of like the beginnings of coordination chemistry. So although the history of bonding and the interpretation of reactions of coordination compounds really begins with Alfred Werner, coordination compounds were known much earlier, and many coordination compounds have been used as pigments since antiquity. So some of those pigments include Prussian blue, So there's a picture of Prussian blue, and that's an iron cyanide compound. This aurelian is a cobalt complex. And this red dye here actually contains calcium in it. And with the gradual development of analytical methods, the formulas of many of these compounds actually became known in the late 19th century. And then once they knew the formulas, then they could learn about the structure and how things are actually put together. So as we start looking at the properties and electron configuration of transition metal compounds, the properties of the transition metals are similar to each other, but they're very different to the properties of the main group metals. The transition metals have high melting points, high densities, they're moderate to very hard, and they're very good electrical conductors. And also, if you'll remember, the transition metals have 2 valence electrons, and also we're filling the d orbitals in the shell below the valence electrons. So if you remember when we did like the scandium and we did the argon and the 5s and the 4d, so the orbitals and the electrons in the s orbital are the valence electrons. So group 1b and some others have 1 valence electron due to the promotion of electron into the d sublevel to fill it. And they form ions by losing the ns electrons first, and then after they've lost all the electrons from the s orbitals, then they'll get the electrons from the d orbitals. So let's look at some of these electron configurations. So we did the scandium, so we said the scandium with a neutral was argon 4s 3d1. But notice, so with each element as we go across the periodic table, we're just adding 1. But I want to draw your attention to chromium and for copper. We have a little bit of a weird thing going on here. So notice as we go from titanium to vanadium, so we go 1, 2, 3, 4, we have 5 electrons. Chromium we're going to add 6, but this time, rather than adding just another electron in this orbital here, we promote electron from the s to the d. And that's because chromium gets some extra stabilization by having everything half full. So chromium is one of those exceptions that you need to know. Now if we're looking at the electron configuration for chromium plus, then the electron configuration for chromium plus would be the argon 4s 0, because we remove an electron from the s orbital first, and then we remove it from the d, but we don't need to remove anymore, so it'd be 3d5. And if we did chromium 2 plus, it would be argon still 4s 0 3d4. So remember, take the electrons from the s first, and then you remove them from the d. And then with chromium and copper, chromium gets extra stabilization by having everything half full, rather than pairing up the 2 electrons and having the 1 vacant here. And then copper also gets extra stabilization by having all the d orbitals completely filled and only having 1 electron in the s, so that electron gets promoted here. So chromium and copper are our 2 exceptions we have to be careful of. And part of the reason why it gets this extra stabilization when we get this shift is because in reality the difference in energy for the 4s and the 3d, they're very close in energy, so it's easy to promote that electron just a little bit. And so we get some extra pairing energy from pairing up and having the d orbitals either completely half filled or completely filled. Now we're going to start looking at some trends, so the atomic size and ionization energy. The atomic radii of all the transition metals are very similar, so for most part they're all about the same, and you have a small increase in size as you go down the column. And for the first ionization energy of the transition metals, they slowly increase across the series, so we have this general increase in the first ionization energy. So it becomes harder and harder to remove an electron. Now, the third transition series, so the third row in the transition series, is actually higher. So notice this green row is above the first and the second row. So what this means is it's harder to remove an electron from a third row transition metal than it is for a first or second row. And this is actually opposite to the trend that we saw for the main group elements, because for the main group elements we said that ionization energy increases as you go across and as you go up the periodic table, whereas here we see the opposite trend with the transition metals. And for electronegativity, the electronegativity of the transition metals slowly increases across a series, except for this last element. So here we have like zinc. So zinc would be our, right here with this blue atom here. So that last column of elements in the transition metals, so actually in the D block, they have a slightly lower electronegativity value. And if you'll remember from our trends from Chem 1A, whoops, that's a bad drawing of periodic table. Electronegativity increase as you go up and to the right and the closer you got to fluorine. And then also electronegativity slightly increases down the column. So as you go down, it becomes slightly more electronegative, and so that's opposite of the trend that we saw for the main group elements. Now here are the common oxidation states for transition metals, or the D block elements, and you'll notice that for just about all of them we have a population here on the 2+ oxidation state. So 2+ and 3+ are very common oxidation states for the transition metal elements. And notice that for manganese, manganese maxes out at +7. So if you think about the electron configuration for manganese, so it's argon 4s2 3d5. So it maxes out at 7 because you're removing all of these electrons here, so that you're removing 2 electrons from the S and 5 electrons from the D. And of course chromium has 1 less electron, so it's maxing out at 6. Vanadium has 1 less electron, so it's maxing out at 5. And that trend continues on. But once you get more than 7 valence electrons, it's harder and harder to remove all of them. Now you have a similar picture in your book. It may vary slightly, but I pulled this figure and I recreated it from Cotton's Basic Inorganic Chemistry book. But you'll find generally the same information. Now lastly, we want to look at some of the shapes and the geometries that we'll see for the transition metal complexes. You'll see a linear complex, so this would be an example with silver and 2 amines. You'll actually make this in lab. You have square planar, so you have 4 things in the plane of the metal, and each of those angles there is 90 degrees. Here is a tetrahedral complex, and a tetrahedral complex has an angle of 109.5. And if there are 6 things bound to the metal center, it's octahedral. So for this, the angles are 90 degrees from each other. These ligands here are in the equatorial plane. So they're in the equator. And the ligands here at the top and the bottom, these are what we call our axial ligands because they're on the axis. So these are 180 from each other. These are 180 from each other, and these are 180 from each other. And the rest of these angles are 90 degrees. So that ends the information for video 1